In this video, we're going to be looking at some important ideas like functions, the vertical line test, and domain and range. This is the first lesson of Unit 1, Functions, as part of my Grade 11 Functions course. If you want me to teach you this entire course, visit my website tutor.ca and enroll in the second teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in Grade 11 Functions. I hope you enjoy the video. Hello everyone, I hope you're doing well. Welcome to the second teacher programs course on grade 11 functions. This is going to kick off the actual content from the course, so welcome to lesson 1 for this course. Hopefully you had a good summer because you're probably watching this at the beginning of September. And so we're going to be talking about similar content to section 1.1 from the textbook that we're following, which again is that McGraw-Hill textbook, Functions 11. And so we're looking at what a function is and these two special properties about functions. So yeah, let's just get into it. Hopefully you're ready. Now, I mentioned this in the introduction video, but I think the idea is that you have some set of the student notes available with you at the same time. So if you're watching this right now and you don't have the student notes with you, I really recommend taking that out and then write notes as the lesson's going on. That's kind of how I've designed this course to be, is that you have the, I'm going to open it up right now. You have the student note open, this one right here, right? Going to go, just a general outline of everything that we have in the course. Right? I mean, everything we have in the lesson, right? And then as we go on, I'm going to be adding little extra details here and there, right? And so it's going to be a beneficial for you to add things to this. I put big margins so you can add things to this, right? So definitely recommend having that out. Physical, maybe you have a PDF editor or something like that on your computer or however you want to do it. But that is definitely part of the learning process here. Okay. So I'm going to break this lesson up into a couple sections, right? So for our first section, I'm going to say lesson plan, okay, is going to be variables. Okay, we're just going to review what a variable is, okay? Relations, okay, and then we're going to talk about functions, okay? Underneath functions, this is the kind of big thing. We're going to talk about the vertical line test, okay? We're going to talk about sets. It's kind of actually a separate thing entirely. So let me just talk about sets real quick. That's a separate point. And then underneath sets, we're going to talk about domain and range of a function. Domain of a function, range of a function. Now, of course, you don't know what those words mean yet. By the end of this lesson, hopefully you will know what these words mean, right? Okay, so let's begin then. And let's start with variables. Okay. So essentially, a variable is, let me just write this out here. So a variable is a symbol, okay, used to take the place of a number, okay? And that number can have additional meaning. I'm going to explain what this means. Additional meaning. So, sure, if I just write the number x, that could be literally any number, right? If I write x here, that's the symbol we usually choose for variables. That could be literally any number, right? But if I say let x describe or let x measure the number of cars in a parking lot, right? In whatever parking lot. Well, now it has additional meaning. It's any number, but it's also the number of cars in a parking lot, right? So usually in math, we like to just think of it as a symbol, right? That replaces a number, or that takes the place of a number that we don't know. But in any practical way of using math, you give that number additional meaning, right? So the giving additional meaning part is that, and the symbol used to take place of a number is that, right? So just the symbol itself is just a number. Okay, so let's just look at an example, right? Usually what we like to do is we like to measure things, right? And so variables are ways we label that. Like we're measuring the number of cars in a parking lot. And so x is the number that's measuring the number of cars in the parking lot. Let's look at other things you can measure. So like just random examples. Other things you can measure with numbers. So like the cost of apples, I have that here. The number of people in the grocery store, right? The speed a car is going, right? The number of minutes past midnight, right? And so, oh, and I have another one here, length of a string, right? So here, we have just a bunch of examples of things that a variable can measure. So the cost of apples could be the variable, I don't know, C for, wow, can't type, C for A. C for cost. Number of people in the grocery store could be N for number, right? It doesn't really matter. An important thing to note here is that the symbol I choose does not matter at all, right? The symbol I choose. I could, X here measures number of cars in the parking lot. But if I say that measures the number of cars in the parking lot, then that symbol, whatever it is, it doesn't have a name. But if I can draw it again, right, then it means the number of cars in a parking lot, right? There's lots of symbols we use in math, and they all don't themselves mean anything. It's just we give them meaning, right? So again, that doesn't have any meaning, except now I've said let that measure this, right? So it's the same as if I chose X, right? X does not have any additional meaning except what I give it. So I give it the meaning of number of cars in a parking lot. Okay, so then we can essentially now move on to comparing variables. Now, comparing variables are things we do all the time, right? So it's going to be moving on to relations here, right? So a relation is a way to relate the values of two variables. You've done this lots of times before, right? So if I look at an example here, right, at maybe your pay, right, your pay compared to the number of hours you worked, right? So yeah, this is how I'm going to do it. I'm going to say let P represent your total pay, right? Let H represent your hours worked, right? So you can imagine that if H is 0, if we can make a little table of values here, right? If H is 0, then your pay is 0, right? So in a way, we've related the two variables. There's a relation here, right? If you work 0 hours, you get paid $0. There's a relationship between P and H here, or H and P, right? If we work 1 hour, then we get whatever our pay is, our total pay is, right? So if you work, for example, I don't know, 24, if you work for 20, let's do a standard one, maybe $15 per hour, right? Let's say that's your pay. Then in 1 hour, you'll make $15, right? In 2 hours, you'll make $30. 3 hours, 45. And you can see we've related H and P here, right? We've shown that there's a connection between H and P. They're not completely separate variables, right? Another good one, right, is temperature. Okay, so temperature. So I'll do it again like how I did it here. So I'm going to say let T represent the temperature on a given day. Well, you know what? Let's just say represent the temperature. And let M represent the number of months past January. Maybe we can try to graph this relation, right? So if I have a graph on the x-axis, I'm going to put the number of months past January. So this is the m-axis essentially, right? Here is 0, right? Here's maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So I'm going to just draw those numbers in. 8, 9, 10, 11, 12. So that's the m-axis. That's measuring how many months past January. So that's February, right? January, February, March, April, May, June, July, August, September, October, November, December, and then January again. So maybe we don't need that last January, but whatever. And then we have a y-axis coming up, but it's not really the y-axis. It's the t-axis, right? It's measuring the temperature that goes up like this. And let's say like 0's here, right? Let's say 0's right there because, the temperature, at least here in Toronto, goes down below 0. And again, let's just say represent the temperature in Celsius. I should just mention that here in Celsius. Did I not spell Celsius right? I did not. So let's say like the lowest you go to is like, we don't have to be specific with our numbers here, right? But in January, it's pretty cold, right? In January, it's pretty close to the coldest. I'd say, yeah, let's just say January is the coldest temperature, right? So let's just say we have a point there. That's the coldest we get. Where's the hottest we get? It's in about August, right? So January, February, March, April, May, June, July, August. August would be right here, right? On the seventh month past January. And then back in January again, well, we'll be back down to our coldest temperature. So you can kind of imagine that the relationship between these variables, if you were to kind of connect the dots, it might look something like that, right? So again, we've related T and M. We've made a relation between T and M. We did it first time using a table of values, right? And then we did it another time using a graph. Right? So that's two examples of how you can relate variables here, right? And so as you can see, a relation, right, is just a way to relate two values. That's why we call it a relation, right? So an important thing to note here is that for any given time, right, for any given time, we have a single temperature. That makes sense, right? For at any month, I guess, you know what, let's just say we're taking the average temperature in the month, right, or in the day, you know, like maybe what, you know, halfway through between 1 and 2, 1.5 is like halfway through February, right? And so these are all the days connecting it. So there's only one temperature for every time that we give it, right? If we say, well, exactly when March begins, right, what's the temperature? Well, there's only one temperature. So let's try to like specify exactly what we mean here. How is T and M, how are they different? There's a special name we give to each of them, and especially here, P, and H, okay? One has a name and the other one has a different name. So the names are dependent. One is called the dependent variable. Okay, and the other one's called the independent variable. ENT. It's an ENT. Well, right? And so now how do we decide which one's which, right? And what does it mean? Well, essentially, the independent variable carries on no matter what. Okay, independent variable carries on no matter what. The dependent variable only carries on if the independent variable carries on. Okay, in a sense, it depends on the independent one. So the amount you pay, the amount you get paid, doesn't just keep increasing. So if I were to ask you how much should I get paid, right, you would probably say how many hours did you work, right? Because you need to know that first before you can tell me how much I should get paid. So what that means is that the pay depends on the number of hours worked, right? How much you get paid depends on how many hours you work. That sentence makes sense. So that's why we call the pay the dependent variable and H the independent variable. And always this doesn't have to be, but this is how we usually do it. The independent variable is graphed on the x-axis, okay, and the dependent variable is on the y-axis, right? Now, a lot of the time in math, we don't actually think about how the technicals of how the independent variable makes the dependent variable go forward, or the dependent variable depends on the independent variable. We don't really think about that. We just think about there is an independent one and there is a dependent one. Doesn't matter if it's because that's how pay works or if that's how temperature works, right? Like the reason this depends on this is because that's how our society has made pay work, right? You work a certain number of hours and you get paid a certain amount. Math doesn't really care about that in particular. Math just cares that we have an independent one and we have a dependent one. Doesn't matter what technicalities make that true. So a lot of the time in math, we just say x and y. And when I say x, I mean an independent variable. And when I say y, I mean a dependent variable. Okay. Similarly here, well, what depends on what? Time goes forward no matter what, right? Time goes forward. So M, the number of months past January, that goes forward. But the temperature, well, if I ask you, well, what's the temperature today? You're going to ask me, when is it? What date? What's the date? And then you could take a guess, right? Or you can look at a graph and try to figure out what the temperature was at this day. So the dependent variable is temperature because it depends on when in the year that we are at, right? Okay, so there we have that. We know what a dependent and an independent variable are. We also know two ways to show a relation. There are two other ways to show a relation, though, right? So let's mention that quickly. So we've talked about table of values. We've talked about a graph, which passes through some points, right? The points themselves is actually a way to show a relation. So if I just left it as 3 points like that, that's really all I actually know, right? Well, I don't even know it for a fact, but that's all I can, guess with some confidence is that in August we're going to be at our max, and in January we're going to be at our min temperature, right? And so points on a grid, so I'm going to say graph slash points on a grid, is also a way to show a relation here, right? You don't have to connect the dots if it doesn't make sense to connect the dots, right? Because what if, here on the bottom we're measuring months past January. You can have half a month. You can have a third of a month, right? So it makes sense for us to think about values between 1 and 2 to make this a nice smooth curve here, right? But what if that x-axis was measuring something like the number of cars in a parking lot, right? Well, then it doesn't make sense to have 1.5 cars. You'll never have 1.5 cars, right? So you'll only have points, right? You won't have a smooth curve that connects it. You'll only have points, right? And so for that reason, right, sometimes points on a grid is the best way we can get a relation. And then kind of the mother of all ways to show a relation that describes all of these things is an equation. Okay, and you have studied a couple equations at this point in your math career. You've studied linear equations, which is an equation in the form y equals mx plus b. And at this point, you've also studied quadratic equations. Okay, which is something, there's a lot of forms you can write it in, so I'll write all of them. Y equals ax squared plus bx plus c. Y equals, there's also a x minus k squared plus p, right? And then there's also y equals a x minus b x minus c. Okay, so there's 3 ways to write a quadratic. I'll just remind you quickly. So these are both standard form, right? So that's called standard form. That's also called standard form. But now there's the 2 other names for this one. So this is called vertex form. And we're going to study a lot more about vertex form in this chapter. If you forget a lot of quadratics, don't worry. This first unit, the first 2 lessons are about functions. The rest of them is pretty much just about quadratics, okay? And maybe working with some other special math properties about them. But so it's really the first chapter is a review of quadratics. And this is factored form, right? That's called factored form. So again, if you have trouble with this, you don't remember this, we do a huge review in this. Pretty much everything except the first 2 lessons in this unit are about quadratics. So an equation can describe these 3 other methods, right? An equation is kind of the best way to do it because an equation can create a table of values. So if I can make some sort of equation that like tells me my pay based on the number of hours I worked, right? I need to know the number of hours I worked to get my pay, right? That's something I need to know here, right? And so we say here, right, that like P is equal to something happening to H, right? Maybe 2 times the number of hours worked, the number of hours I worked plus 5, something like that, right? Now, we won't talk about this particular example. It's fine. It will be a linear equation. But the idea is, right, is that we can make an equation that describes also this graph and also the points, right? That also describes the points, right? If we just put in whole numbers, essentially. Okay, so that's essentially what a relation is, okay? It's a relation. A relation is a relationship between an independent and dependent variable. Okay. And it can be described in those 4 ways. So points on a grid, graph, table of values, and an equation. Okay. I want to mention here that a relation is not can be, I'll just write that here. Can be described by, like I just said, table of values, graph, points, or equation. But a relation is not any one of these things, right? These are all ways to show a relation. So an example I can give to sort of help you understand what I'm trying to mean here is like a story, right? If you have a story, is a story the movie adaptation, right? Is it the book? Is it the theater production of it, right? Is it the, I don't know, audiobook? Is it the, I don't know what else, graphic novel, right? The story itself is not any one of these things. These are all ways to show the story, right? Through a movie, through a book, through a theater production, through an audiobook, through a graphic novel. These are ways to show the story. But the story itself is something a little bit more abstract, right? It's the ideas, it's the characters, it's the plot, right? So just like here, a relation is not any one of these things. These are just ways to show the relation. Through a table of values, through a graph, through points, through an equation. Equation is usually the best way, right? Right. So can I highlight it here? Yeah, equation is usually the best way. Just like through a story, book is usually the best way. You get the most detail out of it. But that's not the only way, right? And that doesn't make the whole story, right? Because, if you do it through a graphic novel, there's more to the story, right? You didn't get the whole thing through a book, right? And so you see here, that's kind of what I'm getting at here, right? A story, these are the ways to show a story, just like these are the ways to show a relation. Okay. Okay, so let's begin now with a function. Okay, so this course is called Grade 11 Functions for a reason, and that's because we study functions the whole time. Okay, and a function, I'm going to start out here right away with an important point. A function, that's our title. A function is a special kind of relation. Okay, it's a special kind of relation. So if you understand relations, you're going to understand functions. In fact, functions are a simpler kind of relations. Okay, they have a very big restriction on them. There's a very big thing that functions have to be that relations don't. Okay, so let's compare two different situations. I'm going to use this graph up here that I did, right? The temperature, right? The temperature that we have, there we go, as the months go by, right? And I'm going to compare another graph here that I'm going to make. My other example is going to be the relation described by y equals the square root of x, okay? And remember, plus or minus here. I'm going to include the plus or minus, okay? So remember that when I say the square root of, 4, right? Sure, that's 2, right? Why? Because 2 squared is 4, right? That's what a square root means. It's like what number squared gives me that number inside the square root. But there's actually two answers, right? There's not just one answer. The square root of 4 is 2, but the square root of 4 is also negative 2, because negative 2 squared is also 4, right? So we actually have two different answers for the square root of 4. And if I were to graph this, right? If I were to take a graph of this, in fact, let's just do it in Desmos to get a better picture here, right? If I go to Desmos here and I have the square root relation. So in Desmos, this is, if you haven't seen, you probably have seen Desmos, but if you haven't seen it, it's a software that lets you type in the equation of a relation and it'll graph it for you, right? So if I say y equals the square root of x, right? Y equals the square root of x. Then we have this relation right here. So the y value is the square root of the x value. So let's go to 4, right? X value is 4. The y value will be 2, right? The thing is that this doesn't account. This is just the positive square root, right? This doesn't account for the negative one. So the full relation would actually be kind of two equations here, right? And it would look like this, right? So what I'm saying is that for an x value of 4, right, the y value is both 2. So let me put that here. The y value is both 2, right? That point there, and negative 2. Because those are both valid answers for the square root of 4, 2 and negative 2. Okay, and carrying on, right? I can do that for all the points here. 3 for 9, x value of 9, the square root is 3, sure, but also negative 3, right? And every point in between, it's hard to find the exact values of those square roots, but it is possible, and they follow the same pattern. So don't worry too much about how we find them, right? Just remember that, the 9, 4, 16, right? These all have nice square roots. And there's two answers, 4 and negative 4, when I write the relation y equals plus or minus square root x. So let's take a look here quickly. I will go like that, maybe take a screenshot like that. And from here, let's take a look at these two relations. Now, they're both relations because I graphed them, right? It's a relationship between x and y. Here, this is a relationship between m and t, right? So I'm gonna again just type what the things are. So let m represent the number of months past January. Okay. Whoa, boy, I spelled type wrong there. And then let me. let t represent the temperature. That's it. Let t represent the temperature. M is the independent variable because t depends on m. T depends on what time in the year. The temperature depends on what time in the year. Here, I'm not going to let y represent something. I'm not going to let x represent something. It doesn't really matter what it represents, right? We're just looking at the relation y equals plus or minus the square root of x. What real life situation would have exactly this? That's not really what we're interested in math, right? I mean, we do some word problems, we do some example problems of using this in real life, but the studying in math is just to get us the tools to answer these real life questions. So there is definitely lots of real life situations that are described by some sort of curve like this, right? Just like the temperature and the time of year is described by a curve like this. But we're not really thinking about that right now. We're looking at the relationship between an independent variable and a dependent variable. That's particularly the dependent variable is plus or minus the square root of the independent variable. Okay, and so now I have to ask a question, right? I'm going to say when x equals 4, right? Or in the case of, so that's when x equals 4 here. I'll do it for this one. What is the y value? Okay, and a similar question for this relation would be when m equals 4, right? What is the t value, right? So starting with the temperature graph, right? When t equals 4, and when I say when t equals 4, whenever I say when x equals something or t equals something for the independent variable, I want you to imagine kind of like a dotted line here, right? What's the y value? Well, that's kind of like what's the height of the graph on this line. So it's gonna be right there. And that height is whatever this is there, right? That height. So close to 0, not the maximum, right? We don't have any numbers here on the y-axis, on the t-axis, right? So we don't really know exactly a number, but it is one number, right? It is only one number. Like I can take a guess, let's say 10 degrees, right? If I were just to take a guess, because that's maybe like 30 or 40. So there we go, right? So it's not 10 degrees and also 5 degrees, right? But when I take a look at this other relation, when I say when x equals 4, what's the y value? Again, imagine this dotted line when x equals 4, the y value, oh, there's actually 2, right? There's both. So the answer here was like, I'm just going to take a guess, 10 degrees. The answer here was 2 and negative 2, right? 2 and negative 2. So there's an important thing here, right? Here, for any time of the year, I didn't have to say 4 months, right? 4 months past January. I could have said anything. I could have said halfway through the 6th month past January, right? For any time of the year, any time of the year, right? There is only one temperature value. Or in other words, in more technical words, now pay attention here, for any given independent value, in this particular case, it was a time of a year, right? There is only one dependent value, which was the temperature. Any given independent value, there's only one dependent value. In here, that's not true. For any given independent value, right? There is 2 dependent values, or none. But the none doesn't really matter. The 2 is what matters, right? So none is from the fact that if I say x is negative 2 here, right? Well, that dotted line never crosses the graph, so there's nowhere that we can assign a y value, because you can't take the square root of a negative number. That's the issue. If I'm setting x to negative 2, that means I want the square root of negative 2. But in the real numbers, you cannot take the square root of negative 2, or negative anything, for that matter. Okay, so this is an example of, well, they're both examples of relations, okay? They're both examples of relations. Okay? This, though, that's a function, okay? And the reason is, right, is because we have a much closer relationship. We're going to say a closer relationship between the variables, right? Okay, and that's why I think that functions are a little bit easier to understand than relations, because it's again, it's a close relationship. So for any given time value, there's one temperature value, right? As time increases, temperature increases, right? Well, that's true for this section. As time increases, temperature increases, and then as time increases, temperature decreases in this section here, right? But they're related to each other in a closer way than a relation here, because here, for any given x value, there's two y values, okay? So we can't say what is the value of the relation when x equals 4, right? There is no one value. But in a function, we can say that. We can say what is the value of the temperature when time equals 4. There is one number. Here we cannot say that. So it's a closer relationship between the variables. That's what a function is. I think we're ready for the technical definition here of a function. So let's take a look. A function is a word used to describe, okay, a special kind of relation, right? Okay. So the biggest issue here is for every independent variable that I'll say in brackets that we are counting, right? And I'll explain what I mean by that in 1 second. For every independent variable that we're counting, there's only a single dependent value that corresponds. And I use the word corresponds a lot in this course, right? So corresponds mean the corresponding y value to this x value is whatever. So here, so like the corresponding temperature to m equals 4 is 10. So I mean, the corresponding y value to this x value is the y value when we're looking at that line on the x-axis, right? This line here, right? So the corresponding y value to 4 is 10. The corresponding y value to 4 is 2 and negative 2. Okay, so there's not one corresponding one here. The corresponding y value to 7 is maximum, whatever the maximum was, right? 40, let's say 40, right? So I use corresponding a lot. And that'll make more sense in the next lesson, I think, because we're going to talk about more specific ways to think about functions, right? So yeah, that's it. So it's a special kind of relation where every independent variable that we're counting, okay? And so, for example, in the square root function, right? We didn't even count this section, right? We didn't even count the negative values, because the negative values, you just can't take the square root of negative numbers. So we're just not counting that. Right? I want to note something here quickly. If I took, y equals plus or minus the square root of x, right? And we have, it looks like this, right? If I just said y equals the square root of x, right? Not plus or minus, just the square root of x, it would just be the positive arm. And that would be a function now, right? If that's our x-axis and that's our y-axis, because then I can say, for 4, what is the corresponding y value? 2. 2, right? And there's only one answer. So now it is a function. Okay? Now it is a function. Okay? And so this is what I mean when I say the square root function. Okay? This is the square root function, right? Because we just take the positive square root here, right? Only the positive one when I say this. But when I say plus or minus, right, that means I want plus or minus, right? So this relation is not a function though, right? Because we get two different y values for every x value, right? If this is an x value that we chose, whatever it is, we get two different y values. If this is an x value that we chose, we get two different y values. We just wouldn't check this x value, right? This x value here, we just wouldn't check it, right? So it doesn't matter. Just like here, we wouldn't check this one, right? It doesn't matter. That doesn't make it not a function anymore. That's not something we're counting. Okay, and I'm going to just define exactly how do we know what we're counting and what we're not in just a second. So that's going to be that's what the domain is. So first we just got to do vertical line test. Okay. So notice here for a function, if I drew vertical lines here, right? For this x value, we only pass through once. For this x value, we only pass through once. The vertical line test, okay, it's a test to apply, or a test you can apply to the graph of a relation to check if it is a function or not. And think about it like this, right? If I can draw a vertical line somewhere in the numbers, in the x values that we're counting, right, and it passes through the graph more than once, it's not a function anymore, because then we have two y values that correspond to that x value. Okay, if you can draw a vertical line anywhere in the x values that we are counting, okay, and it passes through the graph of the relation more than once, then it is not a function. If you can draw a vertical line anywhere and it never passes through the function more than once, then the relation, or I guess I should say, we don't know it's a function yet, so through the graph more than once, then the relation is a function. So let's just apply this quickly, and then I have one more point to make, and then we're going to move on to what I mean exactly. Now I'm going to exactly say what I mean by, what do I mean by this part? We are counting these numbers, right? That we are counting, right? How do I know, how do I define, how do I say what numbers we're counting, right? Because here I'm just saying, well, think about it, right? Think about it. You can't take the square root of a negative number, so we're not counting negative numbers. But what if a function is much more complicated and you don't know what you're counting or not? So we're going to talk about that in 1 second. Let's just do some examples here, right? So if I look at certain relations, like let me just graph a couple relations here, right? I'm going to start with maybe a parabola, right? Y equals x squared. Sorry, I should write y equals x squared there, right? And I draw some vertical line. Why is a number? What? Whoa, what's going on? X equals... Oh. I'll refresh the page. Let's see if y equals x squared, x equals a. Why is it doing that? It seems to already think a is a number. That's strange. X equals 5. And can I make x go between? Okay, there we go. I don't know what was happening there. Desmos messed up on me a little bit. But let me just do that. So there's our vertical line, okay? That's the vertical line that I'm just going to trace across, and we're going to ask ourselves, is there anywhere that this vertical line passes through the graph of the relation more than once? So think about it for a second. You can see here, right there, we are passing through at that point like that. Here, how about I put a point in? So you see, there's our intersection point, that little highlighted point that I put there, right? So if I let this just sort of go across, right? And you imagine, where is this intersection point going? You can see, remember, the parabola goes up infinitely far up to the top there. But does the vertical line ever pass through the graph twice? And the answer to that is no, right? The vertical line will never pass through the graph twice, right? Doesn't matter how far we go to the left, doesn't matter how far we go to the right. No, that vertical line will pass through the graph at only one point. And we're just kind of highlighting that point here, right? So y equals x squared is a function, okay? Y equals x squared is a function. Let's look at another example. Maybe I'll pause this for a second. Let's look at maybe something maybe a little bit more complicated. What about x? Oh, actually, don't worry too much about what I'm typing here. You don't know how to define what I'm writing here, right? But if I zoom in, now we have a circle here, right? And I'm going to need to do square root minus a squared. And I will do, sorry, just going to get this. I just want the demonstration to look proper. So I will just type this. Again, don't worry too much about what I'm typing there. This is just for the sake of the demonstration. So now, if I go like this, you can see that if I draw a vertical line essentially anywhere, I get 2 points. I'm highlighting them again here, that point and that point, right? I'm highlighting these 2 points here because those are the 2 intersection points, except if I go right to the edge and then I only touch once. So you might say to yourself, okay, well, there's somewhere I can draw a vertical line and it only crosses through the graph once. This must be a function. But no. That's not what the vertical line test says. The vertical line test says that if you can draw a vertical line anywhere and it passes through the graph twice, the whole thing is automatically disqualified from being a function. Okay? This is disqualified from being a function. Because in all these places, I can draw a line through the graph and it passes, draw a vertical line through the graph and it passes through the graph twice, right? And again, the reason this tells us if it's a function or not is because then, think about it. If I ask you, for an x value of 0.5, what's the y value, right? What's the corresponding y value? Well, there's 2, right? And so the function, the idea of a function is that you only have one. That's what a function is, that you only have one output. Okay? I shouldn't say output, but there's only one dependent variable for this independent variable. But here there's 2, right? For all these values, there's 2. For this one value, there's 1, sure, right? But for all the rest of them, there's 2. And over here, well, we're just not counting these ones, right? We're just not counting these ones. There's no graph there. There's no graph for these x values, right? It's not like the circle also appears up here somewhere, right? No, that's the circle, right? And so, yeah, that's what we have. So we're just not counting these values. Okay, and now let's go for some a little bit more abstract graphs that I can't really do on Desmos. What if I had something like this, right? What if I did like something like that and like this? Okay, so let's say it just goes straight horizontally forever or whatever in each direction. Is this a function or not? If this was the graph of some relation, is it a function? Well, ask yourself, can I draw a vertical line anywhere and it passes through the graph only once? Okay, so it looks like even though here it might look a little bit close, right? Yeah, that looks okay, right? That it still kind of slants this way, right? So it's not like we're going to topple over each other. But what about right here? Oh, okay, well, my graph's not perfect, but see, there we have 2 intersection points, there and there, for that one x value. So this relation is not a function anymore. Okay, I don't know what the equation of this relation would be. I just drew a random squiggle. But the idea still holds here, right? That just by looking at the graph, I can tell this is not a function. It is a relation. Okay, and then what about, I don't know, something like that. There, right? Well, here, yeah, I can draw a vertical line anywhere, right? Including there, right? And it only passes through the function once. So, right, it is a function. Function, not a function. Now, you're going to hear a lot of times in this course something along the lines of y is a function of x, right? And now what does that exactly mean? Y is a function of x. That's what I'm just going to quickly define right now, and then we're going to talk about this bolded point. How do we describe what we're counting? Y is a function of x means that y is a dependent variable. So there's a lot more underlying words here. Y is a dependent variable. Okay. Which depends on x and only x. Okay. Y is a dependent variable which depends on x and only x. Okay. And the relation between x and y is a function. That's what that sentence means, essentially. Y is a dependent variable which depends on x and only x. Okay, so it's not like temperature depends on time and also the number of mosquitoes in the world. No, it depends on time, what time of the year you're in, right? And so we see that also the relation between x and y, between temperature and time, for example, is a function. Okay, so in that sense, we say that temperature is a function of time. Temperature is a function of time. Right? Or maybe in this example, we'd say the square root of a number x is a function of the number x. Now, I know you can't see what I'm writing. Just give me a second here. Right? So the square root of a number x is a function of that number x. Right? So the relationship between the square root and the number x, right, is a function, right? I should say the positive square root of a number x is a function of the number x itself, right? Okay, so just so you understand what I say when I say, temperature is a function of time, right? What I mean when I say temperature is a function of time, it means that temperature depends on time and only time, right? And the relation there is a function. Or I can say that the height of the CN Tower, let's too specific. The height of a building is a function of, I don't know, how much money they had to spend on the building, right? That might not be exactly correct, right? There's more factors to include there, right? Let me think of another example here for functions. There's lots of real life examples of functions, right? Like the pigmentation of a paint is a function of how many times how many coats of paint you put, right? How colorful your walls are is a function of how many times how many layers of paint you put on the wall, right? If you put one, it's not going to be that colorful, especially if it's like whatever color you had before, right? But if you put 5 paints, then it's going to be very pigmented. It's going to be very striking color, right? So the strength of the color on your wall is a function of how many layers of paint you put on. So hopefully that makes sense, right? Hopefully that makes sense, that sentence that I'm saying there. And if it doesn't, well, you can talk to me. You can email me, book a session. I'm going to mention all that stuff at the end of the lesson, though. Let's move on now to what I mean. Now we're going to talk about sets. Okay, we're going to talk about sets, and we're going to talk specifically about domain and range. Okay, the domain is essentially answering the question, what do you mean? Whoops, that's not the word. What? Oh my god. What do you mean by, I guess, quote inside quote here. What do you mean by points that we are counting, right? Points that we are counting. So, right like that. So that's the domain, and we're going to describe the domain in just a second, right? We're going to describe the range, which is another concept, but a very related concept. But before we do that, I have to actually tell you what a set is, right? Because these are both examples of sets. And now you may not have actually even ever learned about sets yet, because sets are kind of a more abstract thing. In fact, set theory is a very important set of ideas in math, field of math, which essentially builds everything that we know. All the math that we have can be based off of sets. Okay. In fact, everything I say here, underlying it is a bunch of just sets. And so let me explain to you what a set is. It's a very simple concept, but it's a really powerful tool that lets us do a lot of things. Okay. So let's begin. A set is a collection of things where order and repetition does not matter. Okay. So, for example, if I have flowers, right? If I have maybe a yellow, I'm just going to draw them like this. So, yellow flower, a pink flower, a blue flower, and maybe another pink flower. These form a set of flowers, right? Right? These form a set of flowers. The way we write this, is we put these curly brackets around, right? So curly brackets around. Okay. The curly brackets means these enclose a set. Okay. The curly brackets enclose a set. Okay. And we separate the things inside the set by commas. So this separates. Okay. What are the things inside the set called? Things inside the sets are called, these are all called elements. Okay. So the yellow flower is an element of this set. Usually we also actually give sets names. So I'm going to call this, F for flowers, right? That's a set F. So the yellow flower is an element of F. The purple flower, the pink flower is an element of F. The blue flower is an element of F. Because hopefully all these words make sense to you right now. Sets are just collections of things, in particular where order and repetition don't matter. Okay. Usually in math, we're interested in sets of numbers, right? So in math, we're interested in sets of numbers. I'm going to say that. In math, we are usually interested in sets of numbers. Now, actually, the higher level you go in math, you're interested in sets of lots of other more abstract things. Sometimes you're interested in sets of functions. But anyways, that's a topic for a couple years from now. So in math, we're usually interested in sets of numbers. Let me give you an example. Let's look at this set. S is the name I'm giving it. Okay, it's a set because I'm going to start with a curly bracket. Now, don't worry if your curly brackets look a little funny. Mine look funny too, but I just have done a lot of set stuff, so I can draw them like this. This set contains 2, 3, 51, and -5. Okay, how many elements are in this set? There's 4 elements of the set. What are the elements of the set? 2, 3, 51, and -5. In math, we like to replace sentences with symbols because we don't like to write things a lot. We like to write our math ideas more than we like to write our English ideas, right? We want to kind of take away the English from it because the English is such a distraction, right? Having to say 2 is an element of S, of the set S, right? That's a long sentence. It's not that long, but like it's longer than we want. So mathematicians decided, I'm not dealing with this. I'm going to write a symbol that means this. I'm going to teach you the symbol right now. So 2 is an element of the set S. Okay. Well, 2 is already a symbol and S is already a symbol, right? So we don't actually have to replace those. But what we do have to replace is an element of the set. That gets a fancy symbol that looks like this. It's an E, right? It looks like an E. I'm quite certain it is the Greek letter epsilon, or at least a skewed version of it, right? So if I look at Greek letter epsilon, oops, I cannot spell. Now epsilon's slightly different, right? So that's E like that. Now epsilon like that means something in physics, so we don't really use that. But it is essentially a skewed epsilon, right? And it means is an element of the set S. So 2 is an element of the set S. That's a true statement, right? That is true. 2 is an element of the set S, right? Maybe I shouldn't have used S because my S's look like 5s, but anyways, I wrote 5s normally here. So 2 is an element of the set S. What else is an element of the set S, right? 3 is an element of the set S. 51 is an element of the set S. -5 is an element of the set S. Is like, I don't know, -2 an element of the set S? No, that's an incorrect statement, right? The rest of them are correct statements. That was an incorrect statement. -2 is not an element of the set S. Okay. Again, something to note here, order doesn't matter. You can put this in any order and they're all still elements. And repetition also doesn't matter, right? So we don't really care about how many 2s are in the set. What we usually care about is that there are 2s in the set, that 2 is an element of it, right? So if 2 was here twice, that wouldn't change the set at all. In fact, it would be the same set. Okay? It would be the exact same set. Okay. Then before we move on to domain and range, because domain and range are examples of sets, okay? I just want to talk about an important set, right? And it's called the set of real numbers, okay? The set of real numbers, okay? The set of real numbers is a set collection of things, of numbers. It's a set of numbers, which contains all the numbers you know. Okay. Now there are numbers that are outside of the set of real numbers, but I'm going to assume you haven't learned about those numbers yet. So we have essentially what's in the real numbers. Now, first of all, I just want to mention here, the set of real numbers also gets a fancy symbol. Okay. And it looks like this. So it's kind of like 2 lines. Well, essentially it's an R, but with 2 lines, right? 2 backwards here. So how I usually draw it is that, okay? That's how I usually draw my real numbers, right? I usually don't do the whole 2-line thing, right? So I usually go like just a fancy curly R. That's how I do my real numbers, right? So if I mean R, that's what I mean, okay? So I'm gonna say equals R for my writing, just to do it faster. It's an R, it's still recognizably an R, capital R, but it is not just a standard normal R like that, right? It has some sort of like extra curl to it, right? If you are curious, the font that these are written in is called Blackboard Bold. So the Blackboard Bold font is the font that mathematicians chose to write sets, the symbols that represent sets. And so R represents the real numbers. Z with an extra line is the integers. Okay, integers are 1, 2, 3, 4, 5, 0, -1, -2, -3, -4, -5, and so on in both directions. Those are really the only two you actually need to know, the real numbers and the integers. If I put a little plus next to it, right? If I put a little plus next to it, that means only the positive ones. Okay, and so not 0. 0 is not positive. 0 is not positive or negative. And also negative means I only want the negative ones, right? Okay, so now let's look at some things. What is an element of R? Is 4 an element of R? Yeah, 4 is an element of R, right? Is -2.4 an element of R? It is. Is pi an element of R? It is as well, right? It is also an element of R. Every number you know is an element of R, okay? So when I say something like the variable x is an element of R, what I'm saying is that x can be any number. This is kind of what you already mean when you just write the variable x and you say, well, let x represent something, right? X can be any number. But sometimes x can't be any number. Sometimes x can only be an integer. And so we say this at the start. We say x can only be an integer. X is an element of the integers, right? But anyways, most of the time we're going to be dealing with this. This is essentially what we're going to be dealing with. X in R. Sometimes you're going to hear me say XER because that's something, just a habit that I have of saying XER. Because when I do math, people understand what I mean, like when with my friends or whatever, if we're doing math, like people understand what I mean when I say XER. But I'm going to try my best for this course not to say XER. But if you ever hear me say XER, I mean X in R, or X is an element of R. Okay. But you can also read that as XER. So you can either say X in R, X is an element of R, or you'll hear XE, right? As long as you know what E means. It's not an E, it's an epsilon. It's not even an E, right? Kind of looks like an E, though. As long as you understand what I'm saying, then that's good. Okay, so now that we have an understanding of what a set is, of what an element of a set is, the epsilon symbol, the set of real numbers and the set of integers, right? What's in those sets. Now we are ready to talk about the domain and range, okay, of a function. So the domain and range of a function are both sets, okay? Every function has a domain and a range. Okay, every function has a domain and a range. Okay, what is it? The domain, okay, is the set of all the numbers we are counting. Okay? Okay, the range is the set of all the numbers that we can well, okay, before I say the range, actually, you know what, let's focus on the domain for a second. I just decided that right now. So the domain is the set of all the numbers we're counting. Now let's specify exactly what we mean by that. When I have the square root function here, right, and remember when I say square root function, I mean only the positive square roots, right? So y equals the positive square root of x. Okay, this is the y-axis here. Wow, sorry. This is, oh my god. Is my tablet crooked? I think. There we go. That's a straight line. Well, more or less. When I say, what numbers are we counting? We're counting all these numbers, right? And the reason is because the function exists at those x values, right? The function simply doesn't exist here. So more specifically, the domain is the set of all x values, or just independent values, where the function exists, as in there is a corresponding y value for that x value. Okay. So the domain is the set of all x values. This is the actual definition. That is oops, didn't mean to do that. That is the definition of the domain. Okay? The domain is the set of all x values, independent values, where the function exists, as in there is a corresponding y value for that x value. This x value right here, this green line, not in the domain. There is no corresponding y value to that x value. What about this one? That is in the domain. This one too. In the domain? Yep. In the domain? Yep. Because there's a corresponding y value for all these x values. Oh, this one, not in the domain. 0, that's in the domain. Because the square root of 0 is 0. So there is a corresponding y value for that x value. So how I want you to imagine this. This is the best way to imagine how do you figure out the domain and range from the graph, right? What I want you to do is picture this. When you have a function, okay, first of all, understand what's called the end behavior. Understand what this arrow means. It means it keeps going on as you'd expect, right? So the curve is going to keep going like that approximately, right? It's not going to curve down, right? It's just going to keep going flat and, maybe slightly up, but flat. And so the domain, this is how you picture it. Now, this is the technical definition, right? This is the actual definition of the function. But what I'm going to give you right now is a way to think about it, okay? That might not seem so mathy, right? But it will work. It'll help you figure out what the domain is, okay? So let me put this down here, right? What I want you to imagine is that there's an infinitely long fluorescent light bulb on the top here. Remember fluorescent? I'm sure you have them in your school. Fluorescent light. These long tubes, right? The tube lights. There's an infinitely long one on the top there. And our graph is like a solid object. Where would the shadow be cast? The shadow would be cast down here, right? The shadow would be cast onto the x-axis here. All of this would have a shadow. In fact, it would go infinitely. The shadow would be infinitely there. Would it be at 0? Important to check 0, right? If there's something funny happening there, right? Important to just think about it for a second, right? Is there a corresponding y value for that x value? Would a shadow be cast there? Yes, it would. So all of these points are in the domain. All of these points. But no shadow would be cast here, right? There's no graph there. In fact, to be completely correct, there's actually a fluorescent light bulb on the top and bottom, okay? Right? So if this graph, for example, if we have a different example, let me just look at a different example quickly. Right? So if I had something that looks like this, okay? There's our x and y axis. If this was maybe this beginning of a square root function, and then also this, right? First of all, that's a function, right? That's a function. And what's its domain? Well, imagine a fluorescent light here, infinitely long, here, infinitely long, right? Where would the shadow be cast? Well, the shadow would be cast down like this, right? Onto the x-axis for all these points. And it would also be cast down like this, right? From that light, from the bottom light. Right? And again, what this really means is that for like this x value, yeah, there's a corresponding y value because the shadow was cast onto the x-axis at that point, right? So this is how you can think about it, visualize it. I really want to drill in visualizing this stuff here in this course, because I think that's one of the best ways to be successful in math, is to really have a good way of visualizing things. So the domain is, as imagine you had two infinitely long fluorescent lights, one on the top, one on the bottom. Where would the shadow be cast onto the x-axis, right? It would be cast infinitely in either direction for this one, right? So the domain of this function is the whole x-axis. The domain of this function is only 0 and above. So the positive numbers and 0. So I'm going to write that in words here. Domain of this function is 0 and the positive numbers. Okay. Domain of this function is all real numbers. Okay. But first of all, that's not a set. The issue here is that that's not a set. I didn't write that as a set yet, right? So let's write it as a set. How would I write this as a set? Let's start with this one, maybe. The domain of this, well, no, let's start with this one, actually. Let's start with this one. So there's more special notation coming at you here. So you gotta be a little bit ready for this, okay? But I'm gonna rewrite this sentence using symbols. So first of all, the domain of this function, usually we just say D equals. Right? The domain equals a set. What's in that set? That set contains x values, which can be real numbers. Okay? X values, which are real numbers, but not any real numbers. Okay? Now, pay attention. The words I'm saying are the symbols I'm writing. The domain of this function is a set of x values, which can be any real numbers, but x has to be bigger than or equal to 0. And that's how you write that in symbols. X is any real number, but that vertical line means, but wait, x has to be bigger than or equal to 0. Right? And that is what I'm saying here, right? It's 0 and any positive number. X has to be bigger than or equal to 0. That is exactly the domain of this function. Take that in for a second. Okay. Domain of this function. This is the domain of this function, D equals the set, okay, of x values, which can be any real number. That's it. Right? There's no but here. No, it's a set of x values, and they can be any real number. Any x value works here. The shadow is cast onto the whole x-axis. So the domain of this function is all real numbers, and that's it. X values, which can be all real numbers. Okay, so I'm going to remind you, that is the domain. Okay? That is the domain. Right? Is the set of all x values, independent values, where the function exists. As in, there is a corresponding y value for that x value. The range is kind of the opposite. Okay? The range, I'm just going to do this so I can have the same size font. The range is the set of all y values, as in dependent values, okay, where which are corresponding to some x value in the domain. The range is a set of all y values, dependent values, which are corresponding to some x value in the domain. Right? So, let's look at some examples of what that exactly means. If I look at the square root, not square root function, sorry, x squared. Okay? Y equals x squared. That would look something like this, right? You've studied parabolas before, so that would look something like that. What y values are corresponding to some x value? Okay, what y values are corresponding to some x value? So for example, this y value, is it corresponding to some x value? Yeah, it is. To this x value, x1 and x2. Because the corresponding y value to this x value is that y value. And the corresponding y value to this x value is also that y value. So that y value, whatever it is, let's just say it's, I don't know, let's say it's 4, it's whatever, right? That y value 4 is in the range because it corresponds, or it is corresponding to some x value in the domain. In fact, it corresponds to 2 different x values in the domain. That's fine, right? It has to correspond to at least 1, right? So this would be, I guess this would be, the example I use is, it would be 2 and negative 2, right? Because negative 2 squared is 4, 2 squared is also 4, right? So that means that 4 is in the range because negative 2 and 2 are in the domain of x squared, right? So again, domain of x squared, let me just do that quickly on the side here. Domain of x squared. Right, so x squared would look something like that. Now imagine an infinitely long fluorescent light bulb here and here, right? Where would the shadow be cast? Well, this would do actually no casting of shadows because there's no graph in the negative side here, right? But where would the shadow be cast this way, right? Well, it would cast down like this, 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 In fact, anywhere here, and remember, end behavior, this goes on forever that way, this goes on forever that way. So in fact, the shadow would be cast throughout the whole x-axis. So the domain of a parabola, the domain here, is again, x can be any real number, right? X can be any real number. So -2 and 2 are definitely in the domain, and 4 is in the range because it is corresponding to -2 and 2 for this relation. Okay. Again, let me give you a way to think about it. Oh, sorry, and let me do one more example. What about like -5, right? That is not in the range because it does not correspond to any x value. There is no x value that when you square it, you get -5. It just doesn't exist. There is no x value that when you square it, you get -5, right? So, and that's related to the fact that we have no square root of negative numbers. So -5 is not in the range. So to figure out the range, here's another light bulb trick. I don't like calling it a light bulb trick, but let's call it a light bulb trick, I guess. I'm going to use this, why not? So if I have my function, right? My function y equals x squared. Ooh, okay, it's fine. Just trust me, that's a parabola. To figure out the range, imagine two infinitely long fluorescent light bulbs on the left and right side. Now, imagine the shadow that's cast this way, right? Here there's a shadow cast, here there's a shadow cast, here there's a shadow cast, this way as well, this way as well, this way as well, this way as well, right? All of these points have a shadow cast onto them, right? But not over here, right? So this has a shadow cast onto it, and it's 0 too, right? Because 0 is right there. Because it's kind of like pinned in there, right? But not over here, right? Not there. There's no shadow cast there by the lights because there's no graph here, right? So the range is all the positive values and 0. Now, how do we write that in mathy talk, right? How do we write that in mathy talk? Okay, well, the range is the set, range is the set 2, right? It's the set of y values, which could be any real number, but the y values have to be bigger than or equal to 0. And there we go. Okay, let me see here what else I have in this lesson to finish. Okay, so we've been looking at the domain and range from graphs, which is usually the easiest way to deal with this, right? But what if I have let me do one more example first. Yeah, let me do one more example. I'm actually gonna, let me just do this. So here, let me just put that there like that. There we go. So we have our parabola here like this. That is our parabola. Actually, nope, that's not our parabola. That's our parabola. Okay. I'm gonna say that's a y value of 1. Okay. That's the y, that's 1 right there. So I would say that's the point 1. Or let's just make it 2 to so you can see it better. Let's ask, what's the domain and range of this function? First of all, it's a function. It passes the vertical line test. Okay, but what's the domain and range of this function? Well, remember, they're both sets, right? They're both sets. Okay, they both start with something is a real number. Something is a real number. Or sorry, y is a real number, right? So x is a real number, y is a real number. But there's some sort of restriction. We call this a restriction. And more on that a little bit in the next unit, I think. But these are called restrictions, the little extra details we put. Okay. Now, what are the restrictions? Now, the domain, does it have any restrictions? Imagine domain is your fluorescent light on the top and bottom, right? So imagine here, is there any shadow cast onto the x-axis, right? Well, yeah, there is a shadow cast on the x-axis. A shadow cast like that, there, 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 there. So all this, and it would go on infinitely in each direction because this goes on infinitely like that. So there would be a shadow cast there, right? So yes, the domain is just all real numbers. Okay, no restriction. So I can just write that as x is any real number. That's fine for the domain. Now, what about the range? Okay, range is where something gets a little trickier, right? So for the range, we say take your fluorescent lights. Did not mean to do that. Take your fluorescent lights, put them on the left and the right. Okay, infinitely long fluorescent lights. Where is a shadow cast? Shadows cast here, 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 right? Twice. But not here, right? At 2, yeah, shadows cast at 2 as well, right? Because you can also think of it as like what corresponds to, is the y value of 2 corresponding to some x value? Yeah, 0. X equals 0. This vertical line here, x equals 0. It corresponds to that, right? So yes. So the range is, y can be any real number, but y has to be greater than or equal to, not 0, 2, right? We have to be bigger than or equal to 2. So that's the domain and range of this. Okay, now let's take a look at other ways functions can be written, right? Because the function can be written just like the 4 ways a relation can be written. So a function, so remember, a relation can be written as a table of values, set of points, okay, graph, or equation. Okay, so we're going to talk about how do you find the domain and range for all of these things. In fact, to find the domain and range of these guys, it's actually the same. And to find the domain and range of these guys, it's actually the same. We already know how to find the domain and range of a graph, the graph of a function, right? That's what we've been talking about. How do you find the domain and range from an equation? Graph it, essentially. Graph it, right? So graph the equation by hand or on Desmos, right? And then use the method we just described above. Okay, but what about when you have just the table of values and or a set of points? First thing I want to note is that a table of values and a set of points are the same thing. So if you have a table of x, y values, like maybe 1, 5, 2, 6, 3, -2, 4, 1, 5, 0, right? This is the same thing as a set of points, right? So a set of the points 1, 5, 2, 6, 3, -2, 4, 1. I realize my camera's probably covering. 4, 1, and 5, 0, right? That's the same thing. There's no difference here, right? Usually how I draw it, I don't draw it as a set. I usually just say, okay, well, you can just graph the points like that, right? So if you have a set of points, or if you have a table of values, that's the same thing. Okay, but now how do you find the domain and range? Right? Well, you may be tempted, and I'm going to do it just to humor you. I'm assuming people are making a mistake here, but maybe not. You may be tempted to graph these points, right? To see what it looks like, right? 1, 5, 2, 6, 3, -2, and 4, 1, and 5, 0, right? We have all these points here. I'm going to make it a little bit bigger so you can see. Take a screenshot. And then, oh, I'm here. So you may be tempted to graph these points, right? And connect the dots somehow, right? You can connect them maybe like that, and maybe there's like a nice curve like that and like that, right? But you're adding way more to the question by doing that. I never said anything about what was happening at, 2.5, this vertical line here, or at 1.5. I never said anything about that. All you know are these points. First of all, this is a function because look at the domain. Look at the domain, right? The domain are all the possible independent values, right? All the possible x values. So the domain is a set. The set contains 1, 2, 3, 4, and 5, right? The range is also a set. It contains 5, 6, -2, 1, and 0. Don't make this more complicated by making a graph here. You only know these points, and so you can only say something about these points. The possible independent values are 1, 2, 3, 4, and 5, and the possible dependent values are 5, 6, -2, 1, and 0. That's it. That's all you know. And so that's how you find domain and range for a set of points there. So essentially, I just have one more point to make, I think, and that's actually going to complete the lesson. I have just one more little point to make, I think. Yeah. The last point I have to make is actually just an example like this, right? So if I have, the question is the following relation a function? Okay. Now you might say, okay, I'm going to use the vertical line test for this, right? Okay, but let me show you what I'm going to write first. I'm not going to draw a graph. I'm going to draw a table of values. 0, 3, 5, 2, 1, 6, 5, -3, 7, 1. Or 7, 2. Okay. So, is this a function or not? You really got to go to the definition of the function for this one to understand this one. You really got to go back to, let's look back here. What's the definition of a function? Right? So, a function, okay, I will do this. Actually, let's update the definition of a function really quickly. Right? So a function is a word to use to describe a special kind of relation where for every independent variable that we are counting, we can replace the sentence that we are counting in the domain. Right? Okay, for every independent variable in the domain, there is only a single dependent value that corresponds. So let's look at the domain quickly. So the domain is 0, 0, 5, 1, 5, 7, right? Except 5 repeats, so we don't really have to worry about, you don't have to write it twice, right? So the domain is that. Remember I said repetition doesn't matter in sets, right? The range is, right, 3, 2, 6, -3, 2. But again, 2 appears twice there, so we don't have to write it twice. Is there a single dependent value that corresponds, right, from every independent value? Okay, let's look at 3. Let's look at 0, right? 0, the corresponding y value to 0 is 3. The corresponding y value to 1 is 6. The corresponding y value to 7 is 2. What's the corresponding y value to 5? Both 2 and -3. That's an issue. So independent value 5 has a corresponding y value of 2 and also -3. So what that means, if I were to graph this, right, let me erase all these points now, right, we could actually do the vertical line test in a way. It's not exactly how you're expecting it, but in a way. So 0, 3, 5, 2, 1, 6, 5, -3, and 7, 2, right? The issue is that look at this line, x equals 5, right? On that line right there, right? Let me just get this going quickly. Boom, there we go. On that line right there, there are 2 corresponding y values for that x value, right? So it fails the vertical line test. I think the better way of thinking about it is here, and you can just see that 5 corresponds to 2 different y values, and that disqualifies it from being a function because you're supposed to only get 1. So if you say here, like, what is the function, right? What is the value of the function, the y value of the function, when x equals 5? There's 2 answers. We don't want 2 answers. That makes it not a function anymore. So it is not a function. It wasn't a function to begin with. You can still say a domain and range, right? You still have the ideas of a domain and range, right? And I guess I thought it would be interesting to mention one. I know I keep saying mention one last thing, but just is the following, is the, I'll just type it, is the following graph a graph of a function, right? And let's take a look at that graph. I do have to remember the equation for it quickly. It is right here. I got it. I wanted to just show this one because I think it's an interesting one. It has a little history to it. And yeah, I just thought it would be worth the time to draw it. So there we go. That's an interesting one too, but that's not what I'm looking at. There we go. So here we have this graph right here. Don't worry, that's the equation for it, right? That's the equation for it. But not super important what the equation is. Just from the graph, is this a function? Now you think about it for a second and then tell me. Well, tell me. Sorry, can't really say tell me, can you? Can I? But you know, just think about it while I'm setting up the demonstration here quickly, right? Just making the line the right size. So now, can I draw a vertical line anywhere and it only passes through the graph once? Well, I can do it here. I can do it here. It only passes through the graph once, but not here, right? That there, it does not pass through the graph only once. Here, it passes through the graph twice, right? So it is not a function. Actually, no, sorry. Here it passes through the graph 3 times. What am I talking about? 3 times. 1, 2, and 3, right? So this graph is not a function, it's a relation, and it's particularly called the folium of Descartes. Descartes was a mathematician. This xy plane is sometimes called the Cartesian plane, named after him, because he did a lot of work in, let's just say geometry, essentially. And yeah, he was a interesting guy. So here he is, René Descartes. He came up with that folium of Descartes that I was just showing you. He also came up with a whole bunch of other things. So essentially, what we're studying is called analytic geometry. That's the really fancy name for what this course is studying, functions. And he was kind of the founder of a lot of, well, I shouldn't say founder, but he contributed a lot to the field. And so a lot of this course has to thank to him. And so that's why I thought I would mention this in the first lesson. René Descartes is a huge mathematician who did a lot of work for what we are studying right now. Okay, now that concludes our first lesson. So I hope you enjoyed. I hope this was helpful. Let me just write down here. Let's do a little review of everything we did, right? So we started with reviewing what a variable is, what a relation is, talking about functions, sets, domain and range, and specifically a way to think about domain and range, right? That's the light bulb method. Kind of my method. I don't know if a teacher would mention that to you. And then we looked at just a bunch of examples, right? A bunch of examples. So in the next lesson, we're going to look at more techniques we have to understand functions, a way to think about it, right? You might have noticed a few times I said input output by accident, because that's actually how you think about functions usually. And so we're going to talk about that in the next lesson, but really try to understand all the content from this lesson. I hope you wrote down some notes on your tablet or on your piece of paper with the student note that was out here for this, because that's essentially the idea I have for these kind of lessons. And I hope that you get a chance to take a look at the practice problems. Now, I write practice problems to work perfectly with the lesson, right? So that when you watch the lesson, you have a good understanding right after, and you know how to solve these problems. I'm trying to avoid any frustration here, right? And just get some really effective practice in a short amount of questions. I'm not trying to overload you with questions here. Okay. That is everything for today. If you have any questions, you can, whoops, I knocked my T. Not over though, thankfully. just tapped it. You can email me at secondteacherprogram@gmail.com. You can also book a session with me or another instructor. If I can spell instructor, that would be great. By going to the information page for this website, and you can find here, listen to the introduction video if you want to find more information about that, or go to the information page, like I just said. Remember, the idea I have for this course is that you book about 30 minutes a week, right? That's essentially the idea. In that 30 minutes a week, you come to me with specific questions. Prepare yourself with specific questions that you want to ask, right? I don't understand this topic. I don't understand this topic. I don't know how to do this problem. I don't know how to do this, solve this kind of thinking question, right? Or this word question or something like that. And in that 30 minutes a week, that's when we deal with that. Okay, that is everything for today. Thank you so much for watching. I hope you enjoyed. I hope it was helpful. Again, practice problems, book a session, review this stuff, look at your notes, all that. I hope you enjoyed, and I hope you have a great day. Thank you for watching the video. Remember, if you want me to teach you the entire course, visit my website, tutor.ca, and enroll in the Second Teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in grade 11 functions. Have a nice day.